Hey everybody, welcome back to my channel. Today we're going to talk about Chapter 3, and Chapter 3 is all about, if I flip it back, equations in two variables. This is not actually the easiest thing to do, but we're going to do the best we can. Today we're going to start out with the constant rate of change. We're going to take 2 days to talk about the constant rate of change. We're looking for some information on why graphs are helpful, and we got some vocabulary in this one, a linear relationship, and then constant rate of change. We're going to talk about both of those today. And so a quick little vocabulary lesson here. Relationships that have straight line graphs, like the ones on the previous page, even though we didn't actually graph it, are called linear relationships. Linear has the word line right there at the beginning of it. Graphs that you could draw with a ruler, right? You wouldn't have to pick up the ruler. They make a straight line. And one thing you'll always notice about these is there will be a definite pattern to your inputs and outputs, your X's and Y's. And so what we're going to be looking at today is the change between quantities in a graph or in a table, and then we're going to determine what is the constant rate of change. And I'll just read this word for word. It says the rate of change between any 2 points in a linear relationship is the same or constant. Constant is a word that means the same. A linear relationship has a constant rate of change. Okay, let me show you some examples. This is what it may look like on your questions today. They're going to ask you, is this a linear graph, or does this represent a linear relationship? And then it'll ask you, is there a constant rate of change? And so all you need to do is just kind of compare from here to here, right? Just look and see what it's doing. What are we doing to get from 0 to 1? We're adding 1. From 1 to 2, we're adding 1. From 2 to 3, we're adding 1. Okay, looking good so far. Down here on the Y, 0 to 2, we're adding 2. 2 to 4, we're adding 2. All we're doing is some basic adding and subtracting here, right? And so whenever you get done, you compare your relationships here. Look at this. We were always doing 2. For every 2 on the Y, we did 1 on the X. Right here, combination number 2. Plus 2 on the Y, plus 1 on the X. And then same thing right here. Plus 2 on the Y, plus 1 on the X. Is that constant? Is that the same thing every single time? Yes. This is, I'm just going to put a really tiny word, yes. This is a linear relationship. Our constant rate of change would be 2 over 1. When you do your constant rate of change, or you could just put 2, you always do the Y first, and then you do the on top of the fraction, and then you do the X category, the one on the left, on the bottom of your fraction. And so we have 2, the Y was 2, the X's were 1. And so that's really all we're going to do today. This really isn't too bad once you get the hang of it. Let's look at another one. What happens whenever they make it look like this, like more of a real life situation? This is the number of transactions. This is the thing on the left is always the letter X. On the right, you have your balance, like how many transactions you do at the ATM machine, and then what the amount of money is you have remaining on your account. And so I'm going to just clear this out of the way so you can see. What is my pattern going here? I'm doing plus 3 from 3 to 6, plus 3 from 6 to 9, plus 3 from 9 to 12. So this is the X category. The inputs are always adding by 3. Here your balance, this is minus $30. Here's another minus $30. From 110 to 180, there's another minus $30. So is this consistent? Is this constant all the way down? Yes, it definitely is. This is another linear relationship. What is my constant rate of change? Look at what you have here, right? Minus 30 for every 3 transactions. And then right here, another minus $30 for every 3 transactions. And then look right here, another minus $30 for every 3 transactions. This goes first, the Y, the output. This goes first. You have minus 30. You were losing $30 for every 3 transactions. And honestly, we could divide that, couldn't we? Negative 30 divided by 3 equals negative 10. So this person has a constant rate of change of negative $10 for every transaction, right? Every transaction he's losing or she's losing $10. And so that is the constant rate of change on that one. Negative 30 over 3, which is the same thing as negative 10. Okay, let's try another one. Down here, hopefully we're getting the hang of these. Minutes, how many minutes something has been doing. And how many minutes like you're cooking or maybe you're cooling something down. 5 to 10, there's plus 5. 10 to 15, there's plus 5. 15 to 20, there's plus 5. So we're going every 5 minutes. What's happening to the temperature? Minus 5 degrees. Uh-oh, minus 4 degrees. Now I have a problem. Here, minus 4 degrees. Was that consistent? Oh boy, I don't think so, but let me do a double check. Sometimes it'll confuse you when you just go up and down. You've really got to just kind of compare each situation. Look right here. We went down 5 degrees in 5 minutes. And then here, look at this. We went down 4 degrees in 5 minutes. That's a problem. And here we went down 4 degrees in 5 minutes. Was this constant? No, it's not. Because look, here it's 5 over 5, and here it's 4 over 5. So is this a constant rate of change? No, this is not. Is this a linear graph, a linear relationship? No, it is not. See how that was different? We started out doing 5 and 5, and then we switched to 4 and 5. That is not what we're looking for. That is not a constant. For something to be constant, it has to be the same all the way through. All right, every once in a while when they'll want to try to fool you, they'll give you a graph. Don't let the graph fool you. It's kind of the same thing, right? Look where the dot is. 8, this dot is at 8, and you can't really see that's an 80. So you've got 8 with 80. Let me kind of write it in here. My marker's kind of thick. 16 goes with, that's a 60. And then this last dot, 24, goes with 40. This is how many volunteers, it kind of got smeared here. This is how many volunteers you have working, and this is how long you've been working. So if I look at the pattern, what's the pattern going here? Now, is this a line? Of course it is. Look, I can just draw a line through there. So is this linear? Yes. I can tell that it's linear just by drawing a line through there. What I need to do is figure out what the constant rate of change is. So let's look at our pattern here, right? From 8 to 16, here we're doing 8 to 16, we're doing plus 8, plus 8. From here to 16 to 24, we're doing plus 8. So we're definitely adding 8. And then look at the Y category. 80 to 60, that's minus 20. 60 to 40 is minus 20. And so we're doing every time we add 8, we're losing 20 over here. So we're going to do negative 20 over 8. Remember, the Y category has to go first. Our relationship on this one, our constant rate of change, is negative 20 over 8. I could take a calculator and divide that and get an actual decimal. That would be what? 10 over 4, which is 5 over 2. That'd be like negative 2.5 would be our rate of change. Okay, so you see how we're just looking we're looking at these comparisons to see if they stay the same or if they're different. Okay, let me show you one more example, and then I may be done with this, right? So here's a couple examples I made. Here's another one with a graph. Is this linear? Yes or no? Does it have, what is the constant rate of change? Okay, let's actually look and see what these points are, right? This is the point 5, 100. I'm just going to write it right here because it's easier when it's down below instead of being up on the graph. This is the point 10, 10, and it's kind of hard to tell, 175. 10 with 175. And then this is the point 15 with 250. Okay, so let's just do a quick little check. These are counting by 5s, 5 to 10, 10 to 15. So we're counting by 5s on the X category. On the Y category, we're counting by 100 to 75 is 100 to 175 is adding 75. From 250 to get to 250 from 175, that is also 75. You could subtract those in a calculator if you needed help. So look at the change here. The X's went up by 5s, the Y's went up by 75s. So is this linear? Is this constant? Is this the same? 5 and 5, 75 and 75? Yes, it is linear because look, I could even draw a line through there. That's a perfect line, perfectly straight line. And then what is our rate of change? Our rate of change is right here, 75 over 5, right here, 75 over 5. And so 75 over 5, I could actually divide that on my calculator or on Google. If I needed a calculator on Google, 75 divided by 5 is 15. My rate of change is 15, or you could put 15 over 1. That would be fine. Okay, so that's what these will look like in the book. Let me do one more board of examples, and then we'll be done to get you kind of the hang of it. Okay, this is comparing how much time you've been going and how much something costs. And here we go. We're going to do plus 3. This is going to be plus 4. Okay, now don't freak out yet. This is going to be plus 12. Don't have a panic attack because these numbers are different. It's going to be okay. Look at this one. From 15 to 24, that's adding 9. Use a calculator if you're not the best at that. From 24 to 36 is adding 12. And from 36 to 72 is adding 36. Now, off the top of your head, this looks absolutely crazy, and you want to say this is no, because look how nuts all these numbers are different. But hold your horses. It's not just the numbers that you need to look at, it's the relationship between them, right? Look at really what we have. Our first comparison was actually this, right? We added 9, and then we added 3. If I did 9 over 3, just hold on to that, and then look at the next one. The next comparison, we did adding 12 with adding 4. 12 over 4. And then look at the last comparison, 36 with 12. We added 36, we added 12. Look at all these fractions I wrote over here. If we reduce these, if we divide all these, do we get the same answer every time? I think we do, don't we, right? 9 divided by 3, doesn't that equal 3, right? 12 divided by 4, doesn't that equal 3? 36 divided by 12, doesn't that equal 3? I believe it does. So is this linear? Yes, it is, right? It looked a little weird because they jumped numbers on us over here. But is it a constant rate of change? Look at this. It definitely is. The constant rate of change is 3. So most of the time, it'll be nice and neat, like the ones we saw earlier where it's always add 5, add 5, add 5, add 12, add 12, add 12. But every once in a while, they'll get tricky, and they'll give you different numbers, but you need to be really, really sure. Just compare, going all the way across. Are those fractions, if you divide them, are they going to equal the same thing? Okay, and then last but not least, this is how many chairs you have and how much paint you're going to need. From 5 to 10, that is adding 5, right? From 10 to 15, that is adding 5. Over here, from 6 to 12, that is adding 6. From 12 to 18, that is adding 6. See how this is a normal one? It's the same all over the place. This one is really obvious to say yes. It's not as obvious as that last one. That last one was tricky. But if I really wanted to double check, look at what we have. 6 over 5, my constant rate of change, 6 over 5. And look, it's the same thing here. Adding 6 with adding 5. They're both 6 over 5. Could I divide that, 6 divided by 5, and get 1.2? You could put 1.2 if you wanted, but would I be okay with 6 over 5? Yeah, because that is in simplest form as well. Do not make this a mixed number. Do not say like 1 and 1/5. No, 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 no. Just keep it as improper. Okay, guys, so that's going to be our lesson today. I'm going to put some questions on the Big Ideas Math website, I believe. I'll also post it in Google Classroom, so check Google Classroom and figure out where you need to get. If you have a hard time with this, please email me or send me a question, and I will be more than happy to help you. See you guys.